Hello, and welcome to ARR, a show where we discuss this pretty awesome, exciting database called Targetable, which is implemented in a rather peculiar, rather unusual programming style called target style. So what is target style? Target style is a methodology for developing infrastructure software where correctness and reliability is paramount, which is inspired by things like NASA's Power of 10, MISRA C, and other best practices for writing reliable software. Why would you want to use that kind of thing for a database? Well, you probably want your data to be secure. You probably want your database to never crash. And that's why you want to use target style. So this is from our conference, which we held this summer in Amsterdam. And it documents some, patterns and rule of thumbs we use when building Targetable, for example, logical interfaces, how you really want to program not against a particular implementation, not against a particular operating system, but against more abstract interface, which is actually weaker than you provide. For example, when you do networking in a database, you could say, hey, we are running on top of TCP and we rely on TCP's ordering guarantees, on TCP's CRC checksums, and that sort of stuff. But that makes your system less flexible because you cannot migrate it to UDP, and also it makes it vulnerable to, let's say, bugs in TCP or inherent weaknesses in the TCP's checksum. What we do at Targetable, we say like, hey, okay, we actually aren't going to assume that we are running on the TCP. We'll assume very weak message passing semantics. Okay, so basically there is like a lot of stuff here, and the purpose of me going on the stream like this every week on Thursday at 5 a.m. GC is to share some of those specific patterns, not to explain how Targetable is cool, but rather to teach every one of you to build similar systems. Okay, so what are we up to today? Let's try to recall this. We discuss the so-called ARR of Targetable, which is adaptive replication routing. We are trying to solve a problem of how you could, in a distributed system of 6 replicas, replicate data from the primary node to all the other nodes. And our solution there is that we are going to replicate along a ring where a primary is in the middle of the ring. So there are 3 replicas to the left of the primary, 2 replicas to the right of the primary, and the primary tosses 2 copies of prepare to the left branch and to the right branch. And there, in a branch, prepare is just replicated forwards. Now, additionally, we aren't going to make this ring fixed. Rather, once in a while, we are going to run an experiment and try to arrange replicas in a different order. And if that experiment proves to be a success, we are going to switch to that branch. Okay, so adaptive replication road. And what we've been doing last time is that, if I recall correctly, we started refactoring our implementation as a way to understand the code by just messing with it. So originally, we had this route struct, which was a bounded array. And we are changing this route from a bounded array to a proper data structure because, well, bounded array is not super great data structure in Zeek. Okay. Let's see, where are we at? We have, okay. Apparently we need to refactor this route random function. Okay, so let's refresh a bit about how experimental routes work. Okay, so this is a big idea. Once in a while, we run a particular iteration through an alternative replication route. We measure how long did it take to replicate this operation fully on that alternative route, and if it is actually less time than the route we are currently using, we are flipping to that experimental route. A puzzle which I presented to you last time was how to coordinate this experiment. Like, you basically want everyone to agree on which specific route is an experimental route, so that you could actually get a useful data out of there. But if you need to proactively make everyone agree, that means you need to somehow broadcast this experimental route beforehand, and you need to make sure that everyone got the message. So you probably want some retries there, and in general, it's kind of super messy. It kind of makes experiments. This extra coordination makes experiments hard. So there is a very elegant solution there, and the solution is this. We define experimental route at random. So when a replica wants to figure out what is an experimental route, it just tosses a coin and gets some random route. This is, of course, is not great because different replicas might come up with different experimental routes because they're they're all random, and that's kind of useless. But what we can do is that we can make sure that every replica uses exactly the same coin for generating random route. And we do this by initializing a random number, a generator, with op number as a seed. So, okay, in other words, this is a function which takes op number and returns a random route which corresponds to this op number, which is the same across all replicas. Okay, so why do we not have, okay, because we actually implemented this random route last time, so we should just say that, hey, we want to return route random. Okay, yeah. And similarly, we use this PRNG not only to figure out the route itself, so this usage, but also whether we should be running experimental route for this op at all. Okay. So let's see. Okay, now we need to fix fuzzen, which is actually, Oh, okay. This is just unresolved. I was wondering why we are getting error in tests while we're not trying to compile the test, but actually, like, it's just unresolved name. So this is one of a few errors which are ignorantic. Okay. So what errors do we have here? What errors do we want to fix? Well, this is in a replica. Okay, yeah, let's fix the ones in rodent. Replicas, just a stupid typo. Road slice. Okay, we want to replicas. Count is a field. Decode count equal 0. And we do have push method. Okay. History. Okay, so root is just a field here. I feel like we're getting there. We are almost done. Okay. Valid. How do we use valid? Cert or valid rows in view. Replica count. So valid route in view, route in a replica count. Replicas max and the embedded typos. Route activate. Okay, this function I think we haven't looked at yet, so this is okay. So the way this will work is that after we run the experiment, the primary will decide, okay, so route B is actually better, and then it will call this like route activate, which will say, okay, so now route A is actually this route. Or alternatively, when the primary decide, well, this is like what happens on the primary, but also primary should inform all the backups that, hey, the route is now different. So the primary is going to encode the route into U64 number attach this number to a ping message. And the backup, upon receiving a ping from a primary, will see that this ping actually contains a new route and will activate it. And this is a fun thing here because, a ping might get lost, so a backup might not necessarily immediately learn about the new route. But because the primary sends to at least to other backups, even if those backups don't learn about the new route, they will still respond to the primary with their prepare case. And together with the primary's own prepare OK, it will actually be enough to proceed with commits. So while there is a higher chance of brittleness and stormy weather at the moment where you switch from route A to route B, this actually would not affect the commit latency. Okay, so route valid routing view routing replica count. Okay. Okay, this is the one we've fixed right now. Okay, count is just a field right now, very simple. Okay, I think we are probably done with bugs in routing. Well, no. Okay, so this is just replicas, primary position. Well, actually no. It feels like next hop also should be part of our new road structure. So what is up next hop? We want to say, hey, whom we should send our message next. And it can return up to 2 new replicas. And it kind of okay. Can we do this? Without bounded array. Next buffer. Stop buffer. Yeah, actually, assert next hop. I think that's okay. I think this is actually neat. Why pass bounded array if we can just pass a buffer directly? So let's say that we pass and return a result. Okay. So now we don't actually need this type. We get a route for this op, which is either our experimental route or our primary route. We verify that the route is valid, and then we should say return, I think, next hop for this route result buffer. Well, okay, maybe we don't want to make this a method because let's see what reason we are using replica count. And well, we also need standby count. Actually, okay. This is better. So normal replication. So here we just return um, road next hop result buffer. Road replica result buffer. Okay, random valid encode decode. And here we say that replica uh, okay. Okay, then we find the index of the replica. And we also need view here, right? Let's see. Well, okay, let's pass a view here. That doesn't feel like it is too bad. Okay. Well, I guess we could also validate this. Okay. Count size equals 0. Okay. Hop count. Hop count equals replicas. Plus equal 1. So, okay. Yeah. probably makes sense to actually try to read this code. Okay, so we have a road, which is just a permutation. We know the view number, and we know that the primary is in the middle of this permutation. And we know our own index. So we should try to find whom we should stand next to. So let's say that 0, 2, 1, 3, 5. 1, 2, 3, 4, 5. I missed 4. Okay. Yeah. So let's say that this is our permutation. So this is the primary. If you are 1, you send to 2 and 3. If you are 3, you send to 5. If you are 5, you send to 4. If you are 2, you send to 0. If you are 0 or if you are 4, you send to no one. So the rule here is that if you're after the primary, you send to the next one. And if you're before the primary, you send to the previous one. And if you're the primary, you send to the next and the previous one. So we figure out primary position. And then we figure out our own position in this replication. And if we are before and we are greater than 0, we add previous. And if we are after and we are not the last, we add the next one. Okay, then we assert that hop count is not greater than 2, and let's count. Return hops hop count. Okay. So how many people are on Tagbittle team? There is a question in the chat. I mean, that's kind of like easy to answer. We are open source, so you could just see that, hey, there is like 108 contributors. Some of them contributed a lot of code. Some of them contributed less lines of code. So there's a bunch of people here. Okay. So let's get back here. Okay, so let's see. So, okay, that was replication for normal case. When we are not a standby. Okay, does this actually work? Okay, because I don't see where we jump to standbys. Okay, huh. So let me quickly see how this looks on main, because it feels like it feels like there is something missing here. Okay. Oh, okay. So there is one extra case here. So this actually, okay, maybe. Ha ha ha. Think and face. I'm making a think and face here. So okay, so we have standbys. So standbys are replicas which don't participate in consensus. So they don't provide durability. They don't guarantee anything, but they still kind of like eavesdrop on the messages which are sent by the cluster. And the idea for standbys is that they are like a stepping stone to reconfiguration. So when you want to reconfiguration to add a new replica to a cluster, first you add it as a standby. The standby then runs state sync. So it gets all the state it needs from the cluster. And then it actually joins the cluster as a proper member. And that's like this later part is not implemented yet. But the main invariant about the standbys is that they don't affect normal replication. So that's why we don't care about standbys for adaptive routing. We don't want to adjust our routes depending on what standbys do or do not do. And yet we kind of like should replicate messages to them. So the rule we have here is that the first replica in the ring triggers standby replication. So, okay. I guess we should say that if route and replica equals route replica 0, assert then we only, so okay, if we are replica 0, we should replicate to the first standby. So oops. Buffer. We say hops buffer then equal, yep, and then len plus equal 1, and we assert that hops len minus 1 equal yeah, okay. And then we steal and return hops. Okay. Here we say var count equals 0. Oops. Buffer count next standby. Count plus equal 1. Return hops buffer count. Okay. Well, let's actually do this thing. Count equals 0. Count. Count. So we always return this buffer, and we additionally assert that count is less than 2. So on this code path we have 2, on this code path we have 1. Okay, this I think I like. Oh, actually, okay, we could document this. We need to return at most 2 neighbors in application topology. Assume that the route is as follows with primary with view equal okay 7. If our replica is before we and previous neighbor if we are after one we add the next neighbor the primary adds both neighbors. Okay. Sounds reasonable. Okay, we always return. We only return 2 if we are primary and we have at least 3 replicas. Okay. Post replica in the road kicks off standby replication. Standby's replication uses static run topology. Kicks off. Okay. Yeah, kind of like you see, like tag style. I started like hop count equals 1, add 1, and assert that it equals 2, just in case that we messed up. This is kind of like, you know, like some people look at targetable folks and say, hey, like, you know, they use this like memory unsafe language Zig, they're like crazy. They think themselves to be like, you know, super smart programmers, but no, this is actually the opposite. We think about ourselves as like, you know, very dumb programmers, and that's why we kind of like do this like very stupid assertions. And actually, like, you know, now that I wrote it out, I actually realized that this is incorrect, because if we are a solo replica with standbys, then our hop count is equal 0, but and not 1. So this is actually less than 2. Okay, and then we assert that we are less than equal to 2. Okay. Okay, yeah, this I like this. Assert hop count equals 0, increment by 1, and assert it is 1. But well, this is kind of like, you see, this like very fine-grained assertions actually help catch bugs, because like right now we did cut a bug here. And I mean, that was a bug in my understanding, because I didn't consider this case where we have sole replica. Okay, so there is a question in chat. So the question is like, what is the best way to contribute to targetable? And well, I mean, that is a tough question. And the thing is that like targetable is an open source database. We are Apache 2, I think, licensed. Let's double check. What is the license of targetable? I don't remember. I think it is Apache. Yeah, it is Apache. And we don't even require, you know, CLAs when you submit pull requests. So it's like, you know, like true open source, but we are not open design. So we don't try to take advantage of community. We don't really try to encourage people to write database for us. Now, targetable is a product of targetable team, and we follow design decisions which we think are the best. We don't really try to build like community consensus how to build an open source database. Now, targetable is a database the way targetable team thinks you should be building the database. And I mean, we don't really claim with like 100% certainty that we are right. I mean, we might be right, we might be wrong. Like the time will prove if targetable, well, I mean, targetable is already successful, but the time will tell just how successful targetable will be. Which means we don't really optimize our workflow for accepting contributions. In other words, well, kind of like you could send a pull request to targetable, and if it is good work, we'll merge it. But we aren't really going to like handhold and make sure that the pull request is merged. So yeah, kind of like the best advice if you want to really contribute to Target, well, kind of like you might try, but you are in general on your own. We don't give like guarantees that hey, we will try to merge your contribution, and we don't really like optimize something for hey, this is good for contributor to fix. That being said, if your goal is to learn how to build a database, I guess the best way to do that is to just go and learn the part of Target which you think is most interesting to you. And learn it deeply, understand, and you will learn a lot about that. And you will probably also realize that, hey, it's not actually perfect, and it's possible to improve it, and then you could go and submit an improvement. And well, okay, if we also agree that hey, this is an improvement, we will merge it. So that is the question of what is the best way to contribute to Target. And the answer is intentionally there isn't a 10-step manual for how to contribute to Target. You gotta figure this out. But everything is open source, and we try to be, as you see, very open about how we build the software, what are the underlying design rationales, etc., etc. Okay, another great question in chat. Why does Target not follow Zeek's standard style? Why we use snake case names rather than camel case names? And 2 weeks ago, I would say something like, stupid, just some rationale which I conjured out of my backside to give a reasonably sounding answer. But recently, I've actually learned a proper answer to this question. And the answer is that camel case is a spandrel. So spandrel is a word which originally was from architecture, but it seems like architects are brilliant people. They are very good with words. They coin terms like spandrel or pattern for architecture, and then people from other domains who apparently are not capable of effectively using English language, they kind of have an envy of all those words the architects use, and they kind of steal it. So programmers have stolen the word pattern from Alexander's book about patterns in buildings. And spandrel, I think, was stolen by one biologist or anthropologist. Was he Sapolsky? Sadly, I don't remember the name. But basically, the idea of a spandrel is something which is not intentional. Something which is kind of has to be there for structural reasons. In the Gothic cathedral, you have arches. And then you have this space between the arches, which is called a spandrel. And I mean, there is no inherent purpose to the space between the arches, because only the arc itself has a purpose to hold the building. But well, you kind of just have the space between them, and that's called a spandrel. So my claim here is that camel case is a spandrel, because the origin of camel case is in early Smalltalk. So Smalltalk is an old language. And apparently, and by the way, it's kind of again, just so story, so I haven't double checked my references, so I might be wrong that the story is beautiful. Would be a shame if it's not actually true. But anyway, back in the day, we didn't have Unicode, but even for ASCII, we weren't really sure what symbols do we want to assign to the first 120, to the first 256 symbols. And there were different choices. And in particular, Smalltalk programmers had an had an arrow symbol on this keyboard. So you see this like arrow. This is just like a font ligature. I think arrow left. I think I actually have. Yeah, so this is what I'm talking about. So Smalltalk programmers had this arrow key on their keyboard, and they actually used arrow for assignment. So like, in Smalltalk, you probably could write something like assign like 1 plus 2. I'm not sure if Smalltalk had like infix math, but like let's say let's pretend it has it. So we could like assign 1 plus 2 to x. But quiz, like that was like long time ago, so no Unicode. This is like 256 U8 byte base simple coding page, and we don't have arrow in the ASCII. So how is it possible? Well, the thing is that the arrow used the same code as underscore. So let's see, Python port. So underscore is ASCII 95. And in the modern world, we use ASCII code 95 to mean the underscore. For the computers on which the Smalltalk was developed, number 95 meant left arrow, which was used for an assignment, Smalltalk. And Smalltalk lacked underscore. And okay, how you name your functions if you don't have an underscore? Well, kind of like you have to use camel case. You have to use something like op next hop, although you really want to write op next hop, but well, kind of like without underscore, it's not possible to do that, so you do this like camel case. So because Smalltalk was such a fundamental language for object-oriented programming, this naming convention got carried into Java and then into like every other language which was copying Java, like JavaScript. But really, it's like really stupid, because the reason why you do camel case is because you don't have underscore on your keyboard, but we do have underscore on modern keyboards, and we can just use that for much more readable names. Okay, so that was an answer for Ignatius sounded question in the chat, like why target all use snake case? Because this is objectively better, and the Zig standard style is just wrong here. Hopefully they will switch to snake case when they finalize the language and the standard library. Okay, so this was a rather long detour, but hopefully our next hop function works. Okay, we don't have a route count. Well, I'm not going to fix replica, but replica is okay. So, well, and okay, so this is actually like what's one of the important functions. Like this is the actual routing. How you get the actual routing? Well, you like look at your neighbors. Well, follow-up question in chat. You still use Pascal case for types? Yes, we still use Pascal case for types, and really like something like op history should really be called op history, but well, kind of like that we do because traditionally people use Pascal case for types. Okay. By the way, I really like this like story about Smalltalk is just like something I read on Harky News in a comment. So it might be wrong on all kinds of for all kinds of reasons. So I do encourage you to try to uncover that original history. Okay. Let's see. op prepare, op prepare OK, and op finalize. So op finalize is actually the core of our adaptive logic. But let's see op prepare and op prepare OK. So this is like the purpose of these two functions is to start collecting statistics. So when we run op prepare, we are a primary and we say, hey, we've just prepared this op. So this gets our clock ticking for measuring latency. Op prepare OK says that, hey, we now received prepare OK for this op from that replica. So we could actually subtract this time from when we started the prepare and compute the latency. And finally, op finalize. So when we received prepare OKs from all the replicas, we know that, hey, now we have like the full picture of latency for this op for this route, and we could record it. Let's see how this works. Okay, op prepare. We store history for certain amounts of op. So history max is twice the size of prepare queue, which is kind of like just like, just arbitrary limit. It needs only to be larger than prepare queue, and it's not costly to make it larger. So if we have an op, it goes into op modulo history max slot. But the thing is, this slot might be already tracking an op, which was prepared before. And why it is there? Well, like normally we remove the op from history once it is fully replicated, but it can be the case that one replica is unavailable. So we are waiting for prepare OK from this replica, but well, it will never arrive. So we are going to evict this op from history. So that means that we kind of like realize that the history has ended either when we replicate the op fully, so we get prepare OK from every other replica, or when we evict this. And when we evict an op, we kind of like assume that, hey, it took us infinite time to receive it. So that's why we call finalize. Okay, so, but anyway, okay, I think, can we? Can we assert that this is now 0? I think we should be able to assert this. Okay, so anyway, when we prepare, we say, okay, so the op in this slot is like this, and it has the certain timestamp. So if we look at the history back, so we have the op, we have instant when we prepared, and then we have initial versions of prepare OK times, which is latency max and none are present. Okay, when we receive a prepare OK, there is a special case for when we can op 0, which we use as a special marker that, hey, the slot is empty, so we just special case it. We explicitly allow to count for prepare OK from ourselves. Because remember, the cute trick here is that not only we track network latency here, we also include hard drive latency. So a replica might be further away from us in terms of network, but it might actually have faster disk, which adds up to faster prepare OK. And it might be the case that replica's own disk is pretty slow, so it actually shouldn't be counted in the 3 replicas which are required for prepare to get committed. So kind of like in the normal, so what I'm trying to say is that normally you are interested in the 2 fastest neighboring replicas because your disk is fast. But in the case that your disk is slow, you actually are interested in the 3 fastest prepares. So that's why we kind of like also include the time for our own disk write, which is the time where we send prepare OK to ourselves. Okay, so we record this prepare OK, and if we received full quorum for all replicas, then we finalize the op we've replicated fully. Okay, so let's see what is record prepare OK. We can put the latency. If we already received prepare OK from this replica before, we just asserted the latency is higher because we do enforce monotonicity of the clock here. Otherwise, we just say, okay, this is the new latency, which we kept by latency max so that we don't have to worry about overflow. And we set the present bit. Okay, that's it. Okay, now finally. Finalize. So we know that op is finalized, that we've learned everything that there were to learn about this op. And we know that it is everything because either we replicated the op fully or the op was evicted. So probably some of the replicas are completely unreachable. Okay, let's see. We check that the op at the slot is the current op. We check that, hey, we haven't replicated to more than the entire replica. And if we replicate it fully, we check that, hey, actually, we did replicate to everyone. Okay, so let's first see the boring case. If this is not an experimental op. Okay, so I wonder. Okay, so this actually might. Hey. So I wonder if this code is actually more complicated than it needs to be, because you see. Okay, yeah. So actually, when we record, we cannot assert this because we do not reserve the history after finalization, which might be wrong. So that means that we need to handle the case where op is first replicated fully and then it is subsequently evicted. So you see, we only include the cost here if we were replicated fully and we were evicted and we not replicated fully. So in the normal case where you first replicate the op and then you evict the op, you will get equality here and you will only count the op only once, which is kind of like a hokey way to do this. And I would probably say that we should have said something like wrote in history slot equals like just like clear the history here, but well, okay. That's we are already in the middle of a refactor, so we shouldn't do another refactor on top of it. But maybe we should do this. Okay, let's refactor op finalize to 0 the op. Okay, so anyway, we kind of like finalized the op for the first time. We compute its cost. As I have explained you last time, the cost tracks the median, maximum, and sum. And this is kind of like, you know, like on the one hand, it's kind of like, okay, what free statistics can you compute given a bunch of numbers? Well, like median, maximum, sum. But actually, it turns out, like just by magic, there is no like physical law here, that those free statistics correspond to three things which we care about. So median is commit latency. When we get prepare case from half of the replicas, we know that the prepare is committed. So this is the number we optimize first. Maximum latency is the latency for whole replication. So besides the commit latency, we also care that there are no lagging replicas in the cluster. So it might be the case that, like, you know, replication latency is like super fast, but one replica fell behind completely. We want to avoid that, and that is tracked by maximum. And finally, the sum ensures that the middle replicas, which are not the fastest, but which are also not the slowest, also use the fastest and presumably the cheapest route. Okay, so the history cost, we just copy all the latencies to the stack, take only how many replicas we have, sort them quadratically using insertion sort, and then take left leaning median. And again, the fact that it is like left leaning is exactly matches our quorums. Take maximum, take the sum, and return the history cost. Okay. So we were here. Okay, after we got the cost for this op, we go and do exponential weighted moving average to the existing cost. Okay, that's it. Now, the fun part. The op was actually experimental. Okay, so the thing here is that we don't want to run just one experiment because it might be a fluke. We actually want to run two experimental ops. So a pair of ops is either simultaneously non-experimental or simultaneously experimental. That's why in op road B, we actually initialized PRNG with op bit or 1. So we set the last bit of the op to 1. And that means that op and op plus 1, so op, I don't know, 60 and 61 actually are simultaneously experimental or non-experimental. Okay, so we go and iterate op and its pair. Again, like, you know, XOR1 is a pair. And this, okay, so obviously, like, you know, 2 is like a magic constant here. And maybe we want to, like, you know, do 3 ops. And if we do 3 ops, yeah, kind of like it would be less need to, like, you know, do this op, because, like, you know, you can't do just like op plus 1, op plus 2, because you don't know. Oh, okay, so okay, maybe it's not So I think with 3 you would do like this, and +2. But well, okay, anyway. We only care about 2 ops, so we could just say like this. Okay, this is experimental op, and we check whether we have data for both experiments. So if we don't have data for at least one of the experiments, we kind of do nothing. Okay, then we count whether we replicated both ops fully, and then we compute average cost. So here we have average cost between 2 experimental ops, and we also know how many of our experimental ops are replicated fully. Okay, so if we evict the current op because it was replicated fully, and both ops were replicated fully, well, obviously we want to like say that, hey, experiment completed. Otherwise, if we remove the current op because it was evicted, and both ops were not replicated fully previously, okay, so this is like the last chance for us to account for this. Okay, yeah, okay, so that makes sense. So kind of like we want to run experiments for 2 ops. But the thing is, like, by the time we evict one of those experimental ops, we don't have a guarantee that experiment concluded. But, well, we use the data which we have so far, and because we initialize latencies to latency max, it actually means what we want it to mean. It means that like our latency is pretty high. So yeah, and that kind of like is so like when you see that, hey, you are not going to get more data from this experiment, either when both ops replicated fully or when one of them got evicted and previously they were not both replicated fully. Okay, so in this case, if the cost for current B root is less than our new cost average, we say, okay, so now root B is this, and cost average is this. Okay. And I think that's basically it. For the rodent, we only need to read the integration with replica. And okay, we are like slightly over time, but let's push it a little bit. Let's finish this. Okay, so integration with rodent. Well, we notify rodent whenever we change the views. And we also assert that the view that the rodent thinks is the same that we have. Okay, so this feels like to do for us actually. Is this to do? So on ping, if we are a backup, and we receive a ping with the correct view, and the road there is non-zero, then we decode the road, and if the road is so equal, which I think we could say here, equal road B const bool insert count equals back count, or choose name equal u8 replicas 0 count because b replicas b count. Okay, if equal, I like this in this direction. So if the roads are not the same, then we activate the road, which means that we just assign it to A, but we also assert that the history is empty. Okay. Let's see. So, okay, when we receive prepare OK, we notify that, hey, we have prepare OK, using monotonic clock. When we do view change, we do view change. Okay, so on ping timeout. This is interesting. So, on ping timeout, if we actually have a road which is better than road B, than road A, we reset the history, we activate the new road, and we oh dear, is this wrong? Oh, no. Okay. So I was thinking that we not always encode the root. So we encode the root only if we are primary and we are in the same view that we are sending the ping for, because we, okay, that kind of like goes into the weeds, but sometimes we send earlier view for the ping if there is a risk that our view is not durable, that we might crash and restart into the older view. Okay. So, well, I don't want ping view, I want routing. So, okay, when we prepare, we notify the routing that we prepared. And finally, yeah, when we replicate, we do next hop, view change. When we transition to view change, yeah, we also reset history, view change. Okay, so that's it. It's actually pretty simple. So I think now we should pass zig build check. And I think also Rodin. Build test a unit. Rodin. Hopefully. Well, no. Okay, let's. Oh, you know what? We haven't covered tests. And I think the tests for Rodin are very interesting. So we are going to cover them tomorrow. Well, not tomorrow. Next week on Thursday at 5 p.m. UTC. And that's why that is when we will finish this refactor and hopefully submit a pull request. Okay, so that's kind of like was well. I'm really torn. Like every time when there is an episode where I'm just like talking, I was like, oh dear, this is like super boring. People probably want to see live coding, and I'm just like talking. So I want to do live coding. And then next time I do like a little bit of live coding, and then kind of like, I spent most of my time fixing some my stupid typos and don't actually tell a coherent story. Not that I managed to tell a coherent story when I'm not live coding, but I also feel bad. But well, okay. If I had more time, I would write a blog post. The idea behind these episodes is that this is kind of like, very raw, very unprepared. I'm not trying to pretend that this is like some kind of like super high quality production kind of thing. No, this is just like me like really working, really just understanding target at all. This is like very much like not a reality TV show. This is just like reality show, like reality not show. This is how it is. So again, sorry not sorry for jumping around. Okay, so what have we learned / done today? Well, we fully traced this adaptive part in adaptive replication Rodin when we randomly flip a coin to decide whether a route should be experimental or not. For the case where the route is experimental, we actually continue flipping this same coin, which is the same across the replicas, to come up with random route. Then we track statistics for prepares which follow from this route, and when either we evict an op or we collect all the statistics for this op, we update our summary statistics, our average or exponential weighted moving average. Finally, using these stats, we decide whether our road B is actually better than road A. So we kind of like track the best road B. Finally, okay, so this is I glanced over this, but this is important. On ping timeout. Finally, when the time comes to ping everyone, and we have a better route, we do route switching. Why we do this on ping? Well, because when we ping, we actually broadcast the ping. So this is the moment where we want to notify everyone about the new route. And that means that we can switch routes without disruption. And again, even if there is a disruption, it doesn't actually matter because we always send to at least 2 other replicas. But well, if we can minimize disruption, why don't we do this? Okay, so that's it for today for adaptive Rodin. Next time we will finish this refactor and talk a lot about this. Goodbye, and if you missed this on Twitch, no problem. You could always watch this on YouTube. And if you want to see it live, then please join me on Twitch next week at 5 p.m. UTC, live on Thursday. Goodbye.